I'm about to call you Belu. I'm sorry about that. It's not exactly an insult, but at least it's inaccurate. To be growing numbers. All right, I will start. Dearly Father, we thank you for this morning. I thank you again for these students. We thank you, Lord, for your grace each and every day. We thank you that you loved us even when we didn't love you. We thank you that you came to earth and died for our sins if we just accept you. And we just thank you, Lord, for your many, many blessings to us this day, Lord. In your name I pray. Amen. All right, so today I'm going to talk about the inverse and implicit function theorems. Now I'm using function in a grown-up sense of the term. If you read Edwards, he makes a distinction between the word function and the word mapping. He says a function is real valued, but a mapping is it could be vector valued. I just use the word function for a single valued assignment from one set to another. So for me, a mapping is a function. I don't reserve the word function for real valued functions. So keep that in mind as I use this language. So, what's the inverse and implicit function theorems? So let's look at the problem. So what's the problem? You've got a function, f, let's say from some subset u of Rn to to Rn, all right? And so you could say f of x is equal to y. But keep in mind here that x and y are n vectors, right? The question is, when can we solve for x? Right? If I can solve for x, some other function of y, right? If I can do that, this new function g is the inverse function, right? Because then you'd have f, let's see here, g of f of x equals to what? Oh, I don't think I'm being very convincing yet. I'm sorry. Retreat. Sorry, let me think through this a second here. Let's see here. That's f of g of y. What would that be equal to? Yeah, f of x, right, which is equal to y. So usually in this sort of situation, we say g is equal to what? F inverse, right? Now we do need the other composition to hold as well, right? You also need that what? Yeah, g of f of x also needs to be equal to x, right? But this has to be true for what? For each y in the what? Yeah, the range of f, or f of u. No snickering. You guys have grown up. Very good. Let's see here. And this is for each x in the domain of f, all right? Which is what? U, right? So that's the problem. When can you find an inverse for a function from Rn to Rn? All right? So we already know from our experience in math before that this isn't generally going to be possible, right? Let's think about calculus 1. That's one problem. So you got y equals to f of x. Here I honestly do mean f a function, from some set of the reals to the reals, right? When can you find an inverse? Well, we know that you can't find inverse even for simple things like f of x equals to x squared plus 1, right? Like that, game over, right? Because it's not 1-to-1, right? So there's two different outputs, two different inputs which give you the same output. So when you try to go backwards, you can't go single valued, you have to go double valued. But on the other hand, if I pick a point, right? If I pick a point like this one, for example, x equals to 1, right? I know if I zoom in close enough to that, right? If I zoom in close enough to that, the function is injective, right? So if I look at some kind of like open interval about 1, like 1 plus epsilon, 1 minus epsilon, something like that, some little open interval there, then the function is injective. Now, which means then I can find an inverse, right? So basically, I can find f inverse if I restrict f, say, from 1 minus epsilon to 1 plus epsilon. Or I don't like my epsilons. I'm going to use delta. All right, delta, delta. Then this restriction has an inverse, right? What's the inverse there? Well, you know what it is. You say y is equal to x squared plus 1. You solve for x by taking the square root. Of course, in general, the algebra gives you plus or minus the square root of y minus 1. But because of the context, we choose the positive square root, right? So, and also, this is not pre-calculus, so I resist the urge to write all of my functions in terms of x because that's simple-mindedness. I'm sorry, why should all functions be written with the value x? But that's what we insist on in pre-calculus sometimes. So students get this sort of metaphysical attachment to the letter x, as if you don't write a function's formula with x, it doesn't count. Sorry, I'm teaching business calculus right now. I've experienced that. I will not use 7 as a variable with business calculus. There is no context in which it is proper to use 7 for a variable.
But it's also not incorrect. If you define it as a variable.
And so begins this. And so begins the story of how Joe's very special first test was written.
I have no doubt I'm pushing on all of these. He's going to go for it.
Every once in a while, a student says something to me, and it makes me drop everything else I'm doing to write them a special test. Every once in a while. Once a student told me, "You can't make me a different test. I have to take the same test as everybody else, so I don't need to study." And I said, "Oh, I have work to do tonight." And then I crafted him the most.
Should I be scared that
I crafted him.
that I didn't study for you when you were last semester?
You shouldn't tell me that. But it's not terribly surprising though. But anyway, okay, I think I'm getting off track. So that's the inverse, but it's not the inverse for the function, right? It's the inverse for a restriction of the function to some smaller domain, right? And of course, it's a local idea, right? I can't. Delta has to be what? Yeah, delta has to be less. It can't go. Delta has to be less than 1. But you know, this is a calculus class. What is it about the calculus of the function here which allows us to find this inverse? It's always going to be a positive slope, right? So I would argue it's that f prime is continuous. It's continuous near 1, right? And f prime of 1 is not equal to 0. So it's continuously differentiable, and the derivative is non-zero. Which, by the way, means what? That means that you can invert it. You can do 1 over the derivative, right? So that basically turns out to be the criteria for mappings as well. We're going to be able to find an inverse for the mapping from Rn to Rn if if the analog to the derivative, the Jacobian matrix, actually is, well, certainly a sufficient condition is that it's continuously differentiable at the point and that it's non-singular. I mean, continuous differentiability means that you have partial derivatives which are continuous near the point, right, on some open set around the point. The condition that the matrix be invertible, we don't actually need that to check on a whole whole open set around the point. It suffices to have invertibility of the Jacobian matrix at a single point. Now it turns out that if the Jacobian matrix is non-singular at a certain point, because if you assume continuous differentiability, it has to be true, in fact, that the Jacobian matrix is invertible everywhere near that point. That actually kind of goes back to that homework problem we talked about before, the fact that GLN is open. So the Jacobian matrix being a point in the general linear group, there has to be a whole open ball of matrices close to it which are also invertible. In more simple terms, if the Jacobian matrix is invertible at the point we're looking at, it can't jump to be if the Jacobian matrix is invertible at the point we're looking at, it can't jump to be non-invertible really, really close to the point because of the continuous differentiability. The behavior of the Jacobian has to be kind of nice and connected near that point. So here's the theorem. Well, actually, I won't read the theorem yet. Let me just show you the plausibility argument for the theorem. So I'm not going to give you a proof today, but let's suppose we want to find inverse near x naught. So again, we're looking at f going from some subset of Rn to Rn, and we want to find some, let's say, I've used U. Tell you what, let me put domain of f here as to be annoying. So we want to find U, a subset of the domain of f. Sorry. Such that what? If we take f and restrict to that thing, then this is invertible. And I said near x naught, so I'm supposing that x naught is where? It's in this U we're looking for. In fact, I'm going to be greedier than that. I'm going to suppose that x naught is the center of U, and we're going to think of, well, I don't want to say that. I mean, I guess I could say that. U is an open ball, and x naught's the center of the open ball. We could do that, just to keep it concrete. I think the truth of the theorem is a little bit more general than that. But as a guide to our thinking, let's just think U is an open ball, and x naught's the center of it. All right? So, what would you do? What's your first step here? Well, my first step would be say, okay, well, I can write, I can write f of x naught. Well, I can write f of x rather equals to f of x naught plus what? Plus f prime of x naught times what? Where that's a vector, right? Plus some small term, right? So let's say plus some remainder term. I don't know, the remainder term, where that's very small as x goes to x naught, right? Our ability to pinch that thing to 0 is essentially the differentiability of the function. That the function is very well approximated by the tangent. It's affinization, it's linearization here, if you like. And so, since this is just a plausibility argument, I'm just going to ignore that remainder term. All right, we'll just set it equal to 0. Admittedly, I'm glossing over some analysis when I do that. Okay. But anyway, really, we're just solving y is equal to f of x naught plus f prime of x naught times x minus x naught. That is a good approximation to the problem we're trying to solve, right? Replace the nonlinear problem of finding the inverse with the problem of finding the inverse for the linearization of the function. So our goal then is to solve for x. So I get y minus f of x naught is equal to f prime of x naught times x minus x naught. Then what do I do? I would say divide, but we're working with f prime as a matrix, right? So let's say multiply by f prime of x naught what? Inverse, yeah. And so that gives me that f prime of x naught inverse times y minus f of x naught is equal to x minus x naught. I think you're one step ahead of me. I don't think I probably need to write all these steps out for you guys, but I did, sorry. So in short, we have then that f inverse of y, right, which is what we call x in this context, is just equal to x naught.
An emotions that gratitude probably one of.
I'm going to call it the Jacobian of x. So, well, fine, I mean, this notation is kind of gray. It's kind of, and then f prime of x naught, all of that inverse times y minus f of x naught. So I can find an inverse to the linearization near the point, provided the Jacobian matrix is invertible. Right? Now, the actual proof for the actual proof for this is the start of the actual proof. Edwards describes a process of, this is the first approximation to the inverse, and then he shows how to basically use the modification of Newton's what's it called? Newton's approximation? Newton's method. Yes, method is the correct word to put here. So it's a generalization of Newton's method for mappings, where you apply Newton's method at kind of an arbitrary point, and you do it again and again and again. This is the first, well, maybe the second step. The first step is really stupid. It's just the constant, right? But then this is the second step, and you just keep doing it and doing it and doing it, and you get the sequence of functions, and you can show that that limit of sequence of functions converges to something which is itself continuously differentiable and is in fact an inverse for the function. That argument about the convergence of the sequence of functions is somewhat technical and involved, and if I do cover it in here, I'll cover it another day. So I'm showing you the first step in that argument. But this is really the heart of it. Everything else is just kind of just fine print. So, question?
Does this mean we can essentially find the inverse of any function without sections that are
Yeah, it means locally I can find an inverse for a function usually.
Can we then find all those little sections, the localized sections that all together?
In fact, no, we can't get a global inverse just from pasting together local inverses. There's something about the totality of the function which may prevent us from having an honest-to-goodness inverse for the whole thing. For example, if I have f of r theta equal to r cosine theta, r sine theta, right? Then you can, f prime of, r naught theta naught is equal to, what is it? It's cosine theta naught, sine theta naught, minus r sine theta naught, r cosine theta naught. And I should say r naught. R naught. So this is invertible, right? You can calculate, and the easiest way to check invertibility is to check the determinant, right? For you guys, that's a formula. Of course, there's lots of other sufficient conditions. If the columns are linearly independent, if the rows are linearly independent, if the only solution is a zero solution, if they can be written as a product of elementary matrices, less important to us here. Anyway, if this is not equal to zero, then it's invertible. So this is just, well, it works out to r naught because you get cosine squared theta naught plus sine squared theta naught. So basically, everywhere except for where r naught is equal to zero, we have that the Jacobian of f at r naught theta naught is in GLNR. It's invertible. But so what that means, right? Ignoring the origin, I have, and so here I'm drawing the. What am I drawing here? The R theta plane, actually. So I can find an inverse. If you pick a point, I can find some kind of inverse if I don't make this disk too big. When does the disk get too big? Right, I can't involve the origin. That's right. That's saying I can't involve the origin. Yes, I agree. But there's a more subtle issue, and this goes to that global concern you had about, can I piece together these inverses and get an inverse on the whole thing? No, you can't. And so if I make this, if I had another inverse down here, for example, right? Suppose that both here's like a U1, here's a U2, and separately this function's invertible. Here's the deal. If this distance here, if this change in theta, if the change in theta that's realized across the things glued together, if it's greater than or equal to 2 pi, game over. Because you face the periodicity of sine and cosine. They loop back. So it's not 1-to-1, because the angle degeneracy comes back again.
Is it not possible to do something like generalized Riemann surface?
Oh, well, many things are possible if I say take the given domain and codomain and replace them with more abstract spaces. Yeah, I think you can take anything and make it into an injection if you're sufficiently creative. Sure, but if I'm stuck here going from R2 to R2, I can't. This function is not going to give me an inverse that has any theta domain which is more than 2 pi. Now, some of you were thinking about the inverse problem, like f of xy equals to square root of x squared plus y squared. The question, what formula do I put here? Let me say theta. I mean, there are different formulas for this, different places. So there's inverse tangent of y over x for the first and fourth quadrants. But the actual calculation of the standard angle, it's got cases. Right? So this again, if you calculate the Jacobian of this thing, let me just say it's that. What's f prime? It's x over the square root of x squared plus y squared. It's y. Oh, sorry. I'm sorry. This is going to burn up a lot of class time, but you can check this, and you'll again get that when x and y are both 0, you get the only place the determinant fails is at the origin. But again, you face that degeneracy. But this time the degeneracy is not so easily visualized. It has something to do with wrapping more than once around the origin. So you have to limit yourself to like a slit plane, a plane where you've removed a ray from the origin. So. I mean, I suppose you can do that, but it won't be a function. Because you're saying that, I mean, you'll have multiple, how can I say this? It won't be single valued what you're describing. But, I mean, you could do such a thing. Another natural question to ask here is, okay, so what you're telling me is if the Jacobian matrix is invertible, that means we can find an inverse locally. Again, I'm assuming continuous differentiability. Without continuous differentiability of the function at the point, I don't know. It's nastier. But is it automatically the case that if then people are tempted to think, okay, so if the Jacobian is singular, that must mean you can't find it at local inverse. Well, that's not true, actually. And there's a simple example from Calculus 1 to warn you away from that thinking. If you have y equals x cubed, if that's my f of x, then f inverse of x is what? It's the cube root of, well, I'm sorry. Stick with my guns. It's the cube root of y in our current way of thinking. And, so yeah, here's x cubed like that. And the other one, if I was to plot it like that, now here I've plotted y is equal to the cube root of x. And then, of course, the black one is y equals x cubed. They are indeed graphs of inverse functions. They have that symmetry about the line y equals x, right? And yet, when you calculate f prime of x, you get what? 3x squared. And as you can see, f prime of 0 is equal to 0, despite the fact that there, in fact, is an inverse about that point where the Jacobian matrix is singular. So singularity of the Jacobian matrix doesn't necessarily spell defeat. It just means we can't use the inverse function theorem. You have to rely on some other method to possibly find an inverse or possibly not. Okay, so that's the inverse function theorem. What is the implicit function theorem? So I'm going to start with an example, all right? So here's the standard example that I like to use. I think it's useful. So
Don't.
x squared plus y squared equals to 1. One equation, two variables, right? Can you solve for y? As a function of x, right? And you're like, well, yeah, of course, right? We just say y squared is 1 minus x squared, right? And then that gives us y is equal to plus or minus the square root of 1 minus x squared, right? Exactly. How can we have plus and minus that's double valued? Right? We need a single valued assignment. So that's exactly the problem. So, so apparently no, not quite, right? Double valued. But if, on the other hand, we say, well, suppose we want to solve near, let's say, x naught on the circle. Let me give it a name. Let's call it C. Near x naught on the curve, then you can sometimes do it, right? If x naught is what? Well, let me say it's not x naught that matters. It's x naught. Let me talk x naught comma y naught. Let's talk about the point. All right. Near x naught comma y naught. What do we need about x naught comma y naught? We need. How about this? If y naught is positive, if y naught is greater than 0, then clearly the solution we're looking for is just y is equal to the square root of 1 minus x squared, right? On the other hand, where we're looking to solve it, if y naught is less than 0, we get the other solution, right? Those are both functions, right? We've solved for one of the Cartesian variables in terms of a function of the other. What is it that makes that point in between where y is equal to 0? So, I mean, what is it about those points that defies our current investigation? Well, let's draw a picture, right? If you look at the circle, those 2 points, right? 1, 0 and minus 1, 0. if you look at those points, right? If you look at an open disk around those points, there's no way that you can solve for y as a function of x, because those are not the graph of a function. They fail the vertical line test. You necessarily intersect the northern and southern hemispheres of the circle there, because you're at that, right? But what's the calculus? What is making it fail in terms of calculus? The slope, yeah, the slope is indeterminate. How do we capture that in terms of calculus on the defining function for the curve? What is it about this expression that makes those points troublesome? So you're thinking about implicit differentiation? That is true. So implicit differentiation has something that's like 2x plus 2y dy dx is equal to 0, right? So then you get dy dx is equal to minus 2x, oopsie, divided by 0 at those points. Yeah. Intuitively speaking, that's a good answer. So what's the significance of the 2y? It's the 2y that was the problem, right? How does 2y connect to, if I call this thing g of xy, so this is a level curve, right? There's the level function, g. What is the 2y? 2y, this 2y is partial g, partial y. It's the y derivative of the level function. So apparently, if the y derivative of the level function is 0, that signifies the possibility I may not be able to solve for that variable as a function of the other variable. See, because 2y is equal to 0 precisely at these points. Everywhere else, these cases,
They're the patients on med surge. They're the patients coming into the ED. So that just sort of reinforces the reasoning behind.
in the cases we can find a function as the solution. So the implicit function theorem, the problem we're looking at is given an equation or a system of equations, when can I solve for some of the variables in terms of other variables? Okay. Now, the thing I have in a bubble up there, we teach that in Calculus 1. But, and it is somewhat ironical that we teach it there. And the thing is, there's a giant elephant in the room. I mean, and especially here, there's a certain hypocrisy in doing it. Because we've just got done doing these epsilon delta proofs, and it's also very formal and rigorous, and then all of a sudden we're doing this implicit differentiation. What are you assuming when you do implicit differentiation? Y is a function of x. How do you know that? You simply don't have that. You don't really know that in Calculus 1. You're just assuming. So essentially, to do those problems in Calculus 1, you have to assume the theorem, which is proved in Edwards here, the implicit function theorem. It's not too bad, though, because it is almost usually, it's almost always true. And the places where it's not true are the same places where you'll see division by 0 when you go back to this this formal method of implicit differentiation. Actually, the implicit function theorem, when it's properly understood, will justify these calculations. We'll put them on a firm footing. So let me tell you the general problem. So we're going to look at a function g from, say, Rm cross Rn to Rn. In other words, we're going to look at g of x comma y equals to k. So the k is a fixed vector of constants. A fixed n vector of constants. And our goal here is basically to solve for y as a function of x. So what we want to do is we wish to find locally. In other words, so you got g of x naught comma y naught equals to k, all right? You've got some point which is a solution to this system, and you want to find h, which is going to be a function from Rm to Rn, or perhaps a subset of Rm, but such that what? Such that g of x comma h of x is equal to? It's equal to k again. That's just a fancy way of saying that I have solved this system of n equations in terms of x. I've written y as a function of x. I solved for y. Right? In other words, I've solved for y. All right? Now, what is the relation? How does h have to filter through the x naught, y naught? What has to be the relation for between x naught, y naught, and the h? H of what equals what? H of x naught is equal to what? Y naught, yeah. Y naught. Oh, sorry, that's horrible. What's that? You just say, when people ask you if you're a math major, you say, why not? What you should tell them is because it's the only subject which counts. Yes. Yes, yes. I spent some hours looking for the most clever math bumper stickers that could be bought. That was kind of the best one out there right now. I feel like it's a... Why not is... Yeah, I do... It's not bad. It's not bad.
You pulled that one in physics one time, and I don't think anybody...
No one heard it?
Nobody heard it. But
Yeah,
I
yeah.
felt like I don't know what happened. I'm not defending your joke. I'm just saying I really appreciate it, but nobody else.
Yes. Well, the best jokes have an audience of one. If you can tell a joke that only your friend understands in a room of a room full of lots of people, especially even people with similar educational backgrounds, that's like the height of comedy. If you can find an audience of one, you've done something. That is a different phenomena. I don't understand what's going on here. I'm just going to laugh because I know I'm going to fail the test. Yes. That is sometimes not well received by professors here. To what? Two kittens on an inclined roof. Which one slides off first? The one with the smaller mew? Very nice. Horrible, but nice. Okay.
I do this about cats.
So,
Well, it's cats falling off the roof, so it's better.
we can, you can prove this theorem using the inverse function theorem, all right? Or you can also prove this theorem by doing an iterative Newton's method solution. And so when you read the formal statement of the theorem in Edwards and in my notes, I have an extra line which tells you how to obtain the actual solution to this problem, or the inverse function, by taking this constructing this iterative sequence of functions, which at the root of it again is based on taking the given nonlinear problem, replacing it with its linearization, and just doing linear algebra on it. So I'm going to show you that again. And also the other reason I'm doing this now is it helps you understand where this comes from. It'll help us understand how to do partial differentiation for variables which are constrained. Right? In some sense, this is a problem. This is a constraint. This constrains x and y. X and y are not independent when they're subject to this system of equations, right? They're somehow intertwined. All right, so here it is. We have g of xy is approximately, right, g of x naught comma y naught plus g prime of x naught comma y naught times, well, let me write it as a vector x minus x naught, y minus y naught. Now this is kind of a funny notation. That's a m plus n vector. Mx is at the top, n y is at the bottom, right? Now, what is this g of x naught y naught? It's just equal to the k, right? We're assuming that that's a solution. And, you know, if we rewrite, what is g prime? Well, g prime is what? It's partial g, partial x, partial g, partial y. Now that is a sneaky notation that I just introduced. So what is this partial? What does this actually mean? You know, it's partial g, partial x1. Partial g, partial what? How many x's are there? M of them, as in mummy. And then, let's see, how many y's? As in what? Nanny? No, it's as in nanu. Everyone knows this. I've actually never watched Mork and Mindy, so I really shouldn't say that. I haven't earned it. My life experience doesn't enable me to say nanu. If you think about it. There are other words I can't say, but do anyway. Yes, such as isomorphism. Okay, but so this is actually, no, this is a square matrix, right? This is n by n. This has got what? This is n by m, n rows, m columns. This whole thing is what? N by m plus n. Which is good because we're multiplying it by this vector here, which is an m vector stacked over an n vector. This is m plus n. In order to multiply this by that matrix, I better have that size. Otherwise, it wouldn't make sense. Now, my point to you, though, is simply this. Because we have this nice decomposition of the Jacobian matrix for the level function g, we can break it down and rewrite it like this. This is g prime. And I'm getting tired of writing x naught, y naught. If you don't mind, I'm going to call this thing p naught. So g prime of p naught. Oh, I'm sorry. Silence, woman. Oh, wait a minute. That could be taken out of context. Oh man, I got some editing to do. Some of my smartest friends are women. Let's see here, partial. Or should I go the Trump route? No. Partial g partial x times x minus x naught plus partial g partial y at the point times y minus y naught. Now, if we're looking for a solution, what should all of this, I mean, let me, if you will allow me this manga-style comment. What should I put here? I'm sorry, manga. I don't know. I don't speak Japanese, but it should be k, right? We're looking for a solution. So the k's cancel, right? And we're trying to solve for y as a function of x. Now you can do it. So the k's cancel, and then just solve this thing for x, solve for y. Let's see here, y is equal to y naught minus partial g partial y at the point p naught inverse times partial g partial x at the point p naught times x minus x naught. Voila. There is your first approximation or second approximation, depending on how you count, of the so-called h. There's your h, approximately. And what is the condition that we need in order to find such a solution? Invertibility of what? We need the determinant of partial g partial y at the point not equal to 0. It makes sense to take a determinant there. Sad. Because this, of course, is a square matrix, right? Yeah. Right. Now, I mean, and then, you know, the way this is most often used is just the lowest dimensional kind of, the simplest case of this, of course, is just when we have g, you know, of x1, xn equals to some constant k, right? That's the often simple case. So here, you know, g is just a function from Rn to R. And in that simple case, you're looking at a so-called hypersurface, right? It's a surface of dimension n minus 1. If you take an equation, so the example I started with, we just had one equation in 2 dimensions. We get a one-dimensional thing, a curve. If you take an equation in 3 dimensions, you get a level surface. If you take a single equation in 4 dimensions, you get a level volume, and so forth. And so what the implicit function theorem then says here is what? You can solve for, like, what, I mean, let's, you know, get past this notation here for a second. And what does it say? I mean, you solve for what? X sub j as a function of what? Right? X minus x sub j x hat. Hee hee hee. Oh, wait a minute. Yeah. So this would be everything except for x sub j. It's a stupid way to write it, but there it is. That's not quite, operationally that's kind of wrong, but yes, everything, fine. So here's a notation. If you want to omit something from a list, just put a hat on it. So for everything except for xj, what condition do you need near the point? I can't spell. NEAR, near p, such that g of p equals to k. What do we need? Right, partial, yeah, exactly. Partial g partial xj of p is not equal to 0. So for example, when you look at the sphere x squared plus y squared plus z squared equals to r squared, where r squared is a constant, you can solve for x as a function of y and z when? Two x is not equal to 0, right? Near the point where you're looking at, because that's the partial derivative with respect to x. But can I put the projector down? Nathan, are we? Can I put the projector down?
Yeah.
Any questions about what I have on the board? Okay. I have some honest to goodness examples to show you. It's like, I guess the first thing I would think of is, in linear algebra, we solve problems like this, right? Given 5 variables, you want to solve for 3 of them. How do you do it? If they're linear equations, you write down the matrix, you do row reduction, and you use the standard arguments, right? How does that square against what we're doing right now? How does that world of thinking and this world of thinking fit together? Or don't they? I hope they do. Before I get to that, though, here's a kind of more interesting curvilinear example. Come on. Oh, I got to get it on the, there's a mode where I can scroll. I need to reduce my margins or something. Can I still scroll if I'm in read mode? Oh, apparently. Okay, good. All right. I have enabled vertical panning. We have entered a brave new world of projecting, yes, thankfully. I figured out that if you take the camera and rotate it 90 degrees, then you can pan like this. Yes. It was there when we were stuck before. I just had to release the camera and turn it 90 degrees and put it back there. Sad. It's okay, I figured it out. So, yeah, that'll happen. So here's a simple, actually I think this is a somewhat simple example. I have e to the xy plus z cubed minus xyz equals to 2. Can we solve this equation for z as a function of xy near the point 0, 0, 1? All I got to do is note, first of all, you can notice that the function is continuously differentiable. If you take the derivatives with respect to x, y, or z, you get continuous functions of x, y, and z. So we're good to go there. That's one of the things we need. You also need that 0, 0, 1 is actually on the solution curve, is actually on the curve, right? Don't be like me. Don't give students a point which is not on the curve to find the tangent line. Always a bad practice. Don't do that. But this one is, too. And so, yeah, g of z is this. And so gz of 0, 0 is 3, which is not equal to 0. Therefore, there exists a continuously differentiable solution for z in terms of x, y. I didn't actually try to find the solution in this example, right? I mean, it's an existence theorem. I say that, but that doesn't quite do justice to what Edwards gives you. He doesn't just give you an existence theorem. He gives you an existence theorem paired with an iterative approximation procedure to find this sequence of functions which converges to the function you're interested in. Now, as a numerical method, I have a suspicion that it's not optimal. But I don't know. I'm not a numerical methods person, so what can I tell you? You can ask Dr. Wang. Here's a better one, although somewhat simpler. What if we have this set S characterized by x plus y plus z equals 2 and y plus z equals to 1? Problem, for which variables can we solve? So I've got 2 equations and 3 unknowns. I expect that that defines a curve. All right? But that's assuming that these equations are independent, that they both are genuinely reducing the total degrees of freedom 3 by 1 each equation. You could think about more pathological systems of equations where the equations were not independent, where they were redundant. Then you'd have to look for something like the rank of the system of equations to determine how many of them are actually genuinely independent. And it might change from point to point. That's what's the end of this chapter, something called the constant rank theorem. You can look at the Jacobian of the system of equations. The number of linearly independent rows in the Jacobian at the point tells you the number of number of genuinely independent equations at that point. Hence the number of reductions of degree of freedom. That's my intuition. So anyway, getting back to the problem, there's a solution, right? 1, 0, 1. You plug it in, you get 2, 1. Okay, great. There's a solution. And so here's the Jacobian matrix of this system of equations. You can recognize it. I mean, it is exactly the coefficient matrix that we studied in linear. Kind of cool. And then what is the so here's partial g partial xy. That just selects this part of the matrix, right? Which you might recognize. I mean, in this particular thing, I think that's the pivot columns, as it happens. So I do think, obviously that's invertible, so we could solve for z as a function of x and y. Or excuse me, we could solve for x and y as a function of z. It's the other way around. In other words, z is a parameter for the line, which is the solution set here. There's a line of solutions, infinitely many. So y. What if we try to solve for y is equal to a function of x and z is equal to a function of x? Then we'd need invertibility of this matrix. To quote my community college instructor, this dog will not hunt. You can't do that. It's clearly not an invertible matrix, corresponding to the fact that you cannot write y as a function of x and z as a function of x. It's not possible to solve for that variable. I mean, it's not possible to solve for the y and z variables in terms of the x variable. Can't be done. There's a distinction between x, y, and z, as is revealed by the corresponding submatrices of the Jacobian. This is what the implicit function theorem makes precise. Let's see if I have a better example.
That example, isn't x always 1 though?
I think that's kind of the problem, that x is always 1. So how can you possibly write y and z in terms of 1 when y and z are variable? Right. For these problems, there's some kind of simple interpretation for what the implicit function theorem says. After all, we didn't need the full-blown implicit function theorem to study linear algebra. We had boxes of numbers, we did row reductions, and we found all the answers we needed. But we can come back and view what we did in linear algebra in the perhaps illuminating light of the implicit function theorem. I don't know. Here's another one. I have 3x plus 2y minus u, 2x plus y minus v equals minus 1 comma 3. So here I'm looking at 4 variables pinned down by 2 equations. I expect that the solution is 2-dimensional. I mean, I expect to be able to solve for 2 of the variables in terms of the remaining 2 this time. And so again, if I want to, if I want to see if I can solve for x and y in terms of u and v, I need to look at this matrix. If I want to solve for, y and u in terms of x and v, I look at this matrix. Is it invertible? And so you look at the submatrices corresponding to the columns of the variables you wish to eliminate. And depending on whether or not those are invertible, you may or may not be able to solve. This is still the same example. So actually solve for x and for u in terms of y and v, but I think, did I show which ones you can't do? Is there one you can't do in this one? I don't know. If I look at, let's see, if you look here, if I pick this and this, if I pick this and this, if I pick this and, I think that you can solve for any 2 of these This one's very